Number 2. Calculate the currents IA, IB, IC, ID, IE, and IF in the diagram. Very complicated looking, right?
Yes.
But actually it's not that tough. Just start from the beginning, okay? Then you can work forward, okay? So let's look at this diagram here. Okay, using the principle number 1, can you tell me firstly, IA, what is the value for IA? Which junction will you look at?
Junction, the bottom one.
Great. Which is? Okay, great.
Okay, so
what
I think should be IA equals IA plus 3.7 milliampere equals to 8.4 milliampere.
Great. Then you can find IA already, right?
Correct.
Okay, great. 1 mark. Okay.
Yay.
So can we proceed on? Can you find IB?
IB, look at a junction. That means it will be the addition of 3.7 plus 4.7 is it?
Okay. Great. That means IA plus 3.7 equal IB, right?
Correct.
Okay, or you can see that this whole thing is a black box. So IB is directly equal to 8.4.
Correct.
Because 8.4
whatever goes in must come out.
Yeah, great. Okay, 8.4 milliampere. Okay, great. Next part could be a bit tricky. So
Next
how to do?
How to do? Oh,
Can you find IC and ID straight away? Actually can, right? Actually can.
I don't know how to find they are
Look
two
higher.
unknowns. Higher? Example 1.
Okay, what is the okay? Yeah. No, look at the diagram. What?
But how to find ID?
Find IC first.
IC. How to find?
Look higher.
Oh yeah. That means the current is actually 1.3 because it's along the same road, right?
Along the same road. Will there be current increasing or decreasing?
Same. Assuming no energy loss.
Okay, great. So IC equals to no energy loss.
Yeah,
there's nothing to do with energy. There's nothing to do with energy
okay,
here.
that's our point. Yeah, the current is the same.
Yes.
So IC is 1.3 milliampere.
Yes, great. Okay.
So ID.
How to find ID?
Oh, ID will be IB minus IC.
Yes, great.
7.1 milliampere.
Yes, very good. Finally, the last one to get the full marks for this question. Actually, got a IF. Wait, still got 2. Sorry. IE. How to find IE? What's the equation?
IE will be... Oh, I know. Look at the junction, right? The black dot. That means going in is ID. Coming out is IE plus 2.4.
Okay, so IE will be?
ID minus 2.4.
Yes, great. Okay, finally IF should be okay, right?
Everything add together.
What, everything add together? IA plus IB plus IC?
No, 2.4 plus IE, then plus 1.3.
Okay, great. Okay, good. Or you can, it's actually equal to IB, right? Because IB is the total current coming in, right?
Yes.
Okay, great. Okay, good. You got full marks for this example. So,
yay.
Okay, I clap for you. Okay, well done. Okay. Okay, we have just finished example 2. Okay, principle number 1. Okay, repeat again. What is principle number 1?
Total current in equal to total current out.
That's a layman way of saying it. Okay, so it's actually based on conservation of charge, right?
Yes.
Okay, good. Okay, so next we're going to go to the next part. Okay, remember just now I talked about conservation of energy? Okay, so energy cannot be created nor
destroyed.
Okay, can only be converted from one form to another, right?
Yes.
So can we apply this in an electrical circuit?
Yes, of
Okay,
course.
great. Okay, so in an electrical circuit, what provides the energy?
If it's a battery, that means will be conversion from chemical to electrical.
Yeah, that's the supply of energy, right?
Yes.
Okay, then where is the electrical energy used up?
When it passes through any electrical components, for example resistors, light bulb.
So what are the possible energy that can convert to?
Electrical energy to heat, light, sound.
Very good. It sounds like you have a script, but okay. No, it's perfect. Okay, so okay, let's look at this very simple example. Let's say the two sources are just R1 and R2. They could be bulb, they could be radio, whatever. Okay, so in this case, right, what supply energy is the battery, correct, with EMF E. Okay, and the two resistors there. So based on what we know about conservation energy, right, we know that what energy supplied by the battery must be equal to energy taken up by the resistor.
Yes.
Okay, so if I want to formulate equation, what equation can I formulate with the information given?
According to the notes is... Why
The note
IE?
at the notes.
I don't understand
The
it.
note at the notes.
How come on the left hand side is
The
IE?
note at the notes. Please, sorry. Okay, please.
Power supply normally is P equals to VI.
Okay,
So V, in this case, will be the EMF. So P equals to EI.
okay. Great. Okay. So the power supplied by source must be equal to power dissipated by resistor, right? And the power supplied by source is given by IE. Any problem with that?
No, I just said that.
You. Okay. Okay, great. Okay. So this is the power supplied by the source. And the power dissipated by resistor is I squared R, right? You learned this last chapter.
This is the typical. Is this the typical formula for power loss?
Yeah. Okay. You learned I squared R or V squared over R, right? Right? Okay.
Yes.
So in this case, simplifying the equation, you will finally get E equal to V1 plus V2. Which means that the EMF in a closed circuit must be equal to the sum of the potential difference in it.
Mr. Fong, what do you mean by potential rise?
The bell.
You got one more period.
We already got 2 periods gone already. Okay. So E equal to V1 plus V2. So potential rise it.
Yes.
That means the supply energy. That means it's the E. The EMF actually supplies the energy. Okay, that's the potential rise supply. The supply
Is it
energy.
conversion from chemical to electrical?
Yes. Okay, great.
Then potential, how about potential drop?
Potential drop will be the loss of electrical energy. That means it's actually the potential difference.
Okay.
So summarizing this principle, we have principle number 2. In any closed loop in an electrical circuit, the total potential rise equal to total potential drop along that loop. Okay. So in this case, there's only one battery. There's only one potential rise, is E, and there are 2 potential drop, V1 and V2. So you sum them up. It's okay.
Okay.
So are you ready for some example?
Yes.
Okay. Let's look at your page 3, example 3. Okay, I have it on my PowerPoint. Okay, so look at this diagram. There's a battery with EMFs 2 volt, resistance 100, 600, 300. Okay, so you want to find the current inside the circuit I. How to find?
Can apply the formula that we learned just now. That means E equals to IR1 plus IR2.
But there are three resistors.
Or plus IR3.
Can or not?
Yeah. Can.
Why can?
Conservation energy. Energy given by the battery.
What if there are 100 resistor?
Sorry?
What if I have 100 resistor?
Is it the same resistor?
Huh?
Is it the same resistance?
No. Let's say I have 100. So it will be 2 equals to?
2 equals to potential difference of all the resistors.
Yeah, doesn't care, right? Whether it's 100 or 3, right? Right?
Yes.
Very good. Okay, so this is the equation. Then you can find current already, right?
Yeah.
Okay, solve this.
Easy lah, Mr. Fong. Give me a
Okay,
difficult
more.
one.
Okay, then second part, potential difference across each resistor.
Isn't this 2 volt?
Hmm?
Isn't 2 volt?
2
Potential
volt is the
difference.
EMF, but the PD across each of them all 2 volt. Then you will violate your conservation energy. Do you remember?
Oh, yeah. Correct.
Okay, so these 2 volt must be divided between.
Share lah.
Yeah,
You need to
share.
put- Oh, okay, share.
So add up must be 2, right?
Yes.
So what is the PD across, let's say the 100 ohm? How do you find?
R equals to V.
Yeah, great. So apply Ohm's law.
Yes.
So you get the answer, 0.2.
Yeah.
Great. How about 600 ohm?
1.2.
Great. Then finally,
0.6.
add up will be?
2.
Great. Okay, this is sounds a bit easy for you. Let's do an example. Which one should we go now? Let's do an example. Can we skip example 4?
Okay.
Let's do an example 5, okay?